Before Gutenberg, a book was not simply written. It was made, page by page, hand by hand, community by community. Monasteries played an important role in copying and preserving texts, but they were not alone. Universities, urban workshops, courtly households, stationers, binders, illuminators, and readers all helped texts move through medieval Europe. A manuscript was never merely an object. It was a record of labor, correction, exchange, and use. A scribe could make a mistake. Another hand could correct it. A reader could add a note in the margin. A binder could join separately copied gatherings into one volume. The history of print did not begin in Europe. In China, woodblock printing had been practiced for centuries. During the Song dynasty, Sheng developed movable type. In Korea, metal movable type appeared before Gutenberg's lifetime. These were not footnotes to a European story. They were major achievements in the history of text technologies. Exactly how such knowledge traveled or did not travel between Asia and Europe remains uncertain. What matters here is simple. No one person invented the idea that written signs could be reproduced. In the middle of the 15th century, in Mainz, Johannes Gutenberg helped establish a remarkably effective European system for print production. It joined several elements: reusable metal type, a method for casting many similar pieces, oil-based ink suited to metal, a press capable of applying even pressure, paper and vellum, skilled labor, capital, and careful organization. Gutenberg did not invent printing everywhere. He did not invent movable type globally, but the workshop associated with his name helped make a new form of European book production viable at scale. The important unit was not language itself. It was a physical piece of type, a small, reusable block carrying a raised character. A compositor selected pieces from a case, arranged them into lines, and locked the lines into a form for printing. When the job was complete, the type could be distributed back into its compartments and used again. Even the Gutenberg Bible, one of the first great European books made this way, still left headings and initials to be completed by hand. Print did not erase craft, it reorganized it. This is the real transformation, the repeatable page. A manuscript copied by hand could be reproduced, but each copy involved a new act of writing. Metal type made it possible to compose a page, print many impressions, dismantle the page, and reuse the same material for another text. The result was not perfect uniformity. Early printing contained corrections, variants, hand coloring, uneven papers, and changing editions. But it changed the economics of copying and the rhythm of circulation. Books, pamphlets, broadsides, maps, calendars, and images could now move through European cities in new quantities. Print helped arguments travel farther and survive longer. It intensified religious controversy, scholarship, administration, commercial communication, and public debate. But no machine causes history by itself. The Reformation, the Scientific Revolution, Enlightenment thought, and later democratic movements had many causes: political conflict, religious institutions, trade, education, war, law, social hierarchy, and human choice. Print changed the conditions under which ideas circulated. It did not write the rest of history alone. The typesetting case invites a modern comparison. Its compartments hold a limited inventory of signs. The compositor chooses, orders, and recombines them to make a page. That resembles later interfaces for selecting symbols, typewriter keys, keyboards, and digital character sets. But resemblance is not dissent. A typecase is not a computer memory register, and Gutenberg's workshop is not the ancestor of every digital machine. The more interesting point is that information systems often depend on agreed signs, reusable components, trained operators, and rules for arranging them. Later technologies developed along several different paths. In 1801, Joseph Marie Jacquard demonstrated a loom controlled by chains of punched cards. The holes directed the loom's operations and allowed complex textile patterns to be repeated. The loom was not a general-purpose computer, yet it showed how instructions could be stored materially and replayed. Charles Babbage later imagined punched cards for his analytical engine. Herman Hollerith used punched cards in tabulators for the United States Census of 1890. His company entered the corporate lineage that later became IBM. These are connected histories of control, data, and machinery, but they are not a single straight road from Gutenberg. Digital text required another layer, encoding. In the 1960s, ASCII, the American Standard Code for Information Interchange, provided binary patterns for English letters, numerals, punctuation, and control functions, so computers from different manufacturers could exchange text. ASCII did not translate every language, and it did not reproduce Gutenberg's particular letters. It was a standard designed for a specific technical world. Later standards, such as Unicode, widened that representational field. The lesson is not that all writing became binary. It is that different institutions agreed on ways to make some symbols machine-readable. More than 2 centuries after Gutenberg's press began transforming European book production, Gottfried Wilhelm Leibniz pursued different questions about calculation and symbolic reasoning. He developed binary arithmetic, a way of representing numbers with 0 and 1. He also imagined a characteristica universalis, a universal symbolic language in which certain kinds of reasoning might be made more calculable. And he designed a calculating machine capable of arithmetic operations. These were ambitious projects, not one completed system. Leibniz did not prove that every thought, every concept, or the universe itself could be reduced to 2 symbols. His dream was larger, stranger, and unfinished. From movable type to punch cards, from character standards to contemporary language models, we can trace recurring questions. How do symbols become repeatable? Who decides what counts as a valid sign? What is gained when information is standardized? What disappears when a system treats words primarily as units to sort, transmit, or predict? The historical answers differ. A printer assembling type, a census clerk punching a card, and a machine learning system generating text do not do the same thing. But each belongs to a world in which symbolic forms are organized for use at scale. AI has not completed Gutenberg. It has introduced a new problem. Printing made texts easier to reproduce and circulate. Contemporary systems can also classify, summarize, translate, and generate text at extraordinary speed. That power does not settle what a text means, whether it is true, who is responsible for it, or how it should be read. Those questions remain human and institutional. They belong to writers, publishers, teachers, readers, archivists, engineers, laws, and communities. Gutenberg's achievement was not the mechanization of the human mind. It was a transformation in the material practice of copying, reusable type, repeatable pages, and a new scale of circulation. Its legacy is not a simple line to artificial intelligence. It is a question that returns whenever a symbolic technology grows powerful, when words can travel farther, faster, and in greater quantity. What new forms of care, judgment, and responsibility must travel with them?